anybody have any questions from the homework? Anything that was weird? I'll admit some of the answer key questions are, or the answer key answers are a little off. Like I think one of them listed E as an answer, yet there wasn't an E. So if there's any weirdness there, let me know. We try to fix them, and then sometimes those fixes don't transfer to the next class. So if you see any issues, you're like, oh, I don't understand why that's this answer. It may be an error, but we can also go over it. So let me know. The quiz that you guys are going to have on Thursday should cover anything from that. So 22 through 24. Okay. So ionic bond strength. What's next? Oh, whether something's a metal, non-metal, semi-metal, generically by electronegativity, and then the bond type triangle, trying to gauge what kind of bonding you have from the average electronegativity and difference in electronegativity. And you don't have to memorize any electronegativities other than the trend, but if you need to calculate something, I'll give you those electronegativities. Don't worry, So, and I mentioned the bond type triangle. I'll give you an outline of a bond type triangle, so the lines will be there, the axes will be there, and you'll have axis labels, but nothing else. Okay, so the regions won't be labeled. You'll have to know what are the regions and so forth. Okay. So, all right. I think we went over some of this stuff. So, let me skip forward a little bit. So we started looking at how to talk about this. You know what? One more thing. Hold on. Forgot to make sure the cameras are. Oh, they're not too bad. I'll leave it for now. So we started to look at the structures of, or started talking about how to talk about the structure of metals, and we're going to get to ionic compounds, anything crystalline. So we started coming up with this idea, well, we're going to treat everything as a sphere. We're going to talk about things having nearest neighbors. Remember that these are large extended structures, so even though we're talking about a very small number of atoms at a time, this repeats quite a lot of times. So we're talking about tons of atoms, 10 to the 23 atoms sometimes. For metals have few valence electrons available for bonding, and those valence electrons are loosely held. Okay, we talked about this. And then we started coming up with this, so how do we define a structure? And to define a structure that repeats, we need to find that smallest repeatable unit that we can draw once and say, well, everything else looks like this. This is what we call the unit cell. So when you define a unit cell, it has to be like every adjacent unit cell with no gap in between has to be exactly the same. That's how you define a unit cell. So we looked at 2D structures, and we did all this. We talked about coordination number, which is exactly the same as the number of nearest neighbors, and you saw that in the lab today. You did coordination numbers for different metals. Some were 8, some were 12, some were 6, I think. The coordination geometry is just a reference to how you describe that arrangement of atoms around a central atom. And we only know octahedral right now, but we'll learn some other names later. And we did the 3x3 square of pennies. So again, pay attention to nearest neighbors. Like there's some that are directly touching, there's some that are close but not directly touching. So nearest neighbors is the closest possible ones. All right. So sometimes you're looking at a space-filling model where the atoms are shown according to how big they are, how much space they take up. Sometimes you're only shown like a ball and stick model. So even though they're not touching, we're looking for the closest ones. And that was what you saw in lab today. You kind of made that sphere get smaller until everything disappeared except for the smallest one, or the middle one, and then you made it one click bigger, and those were the nearest. Okay? So for the pennies in the 3x3 grid, two-dimensionally, there were only 4 nearest neighbors. We called that square. Okay. So here's where we start bringing in a little bit more mathematics. We're going to talk about something called packing efficiency, and we're going to start with 2D and move up to 3D afterwards because it gets a little hairy. So let's start with 2D. And what packing efficiency is the area of the unit cell that is covered by atoms, in 2D at least. When we talk about 3D, we'll talk about volume. But for 2D, this is the area. And remember, when we talk about a unit cell, these 4 atoms are the points of the unit cell, this particular unit cell. But the unit cell is only defined by what's inside this box, right? Because adjacent unit cell would be the next 4 atoms, which these 2 are shared with the next unit cell, okay? So just what's inside the box. So you can see already that some of that is covered by atoms and some of it's empty space. So we're going to calculate that empty space. And the way you do that is, it's pretty simple. I mean, just this equation is simple, but it's not that simple to do. You need to know the area of the unit cell. That's the denominator. And if you know the length of the side of the unit cell, well, this is a square. This particular unit cell is a square. So length times width, height times width, whatever you want to call it, that's the area. So S squared would be the area. So if I know the length of one side of the unit cell, I can get the area. But we're going to actually talk about the length of a unit cell in terms of the atom radius instead. So when I look at an atom, the radius is from the center to the edge of the atom, okay? So we'll talk about that and say, well, I'll show you how that works. So let's do one example before we do number 15 in the chem activity. Does anybody not have this yet? Not purchased it? Everybody has it? Okay. So I believe it's on page 28 or 27 or something like that for you guys. So we're going to do the example first before we do the actual question 15. So here's the example. And the example's worked out, but I want to kind of go over it on the board and make sure it's clear. So we're trying to find the numerator, the area of the atoms on top, and the denominator, the area of the unit cell. So let's do the denominator first, the area of the unit cell. Well, if I know S, the area is going to be S squared, S times S. But I don't want it in terms of the area of the unit cell length. I want to do it in terms of the radius of the atoms. And in this particular arrangement, if you see, S is actually 2 radiuses long. These 2 radiuses are right butting up against each other. So S, the length of one side of the unit cell, is 2r, 2 radiuses. So the area is going to be 2 radiuses squared. 2 radius times 2r times 2r. Length times height. So the area is 4r squared. That's our denominator. That's the area of the unit cell with respect to the radius of the atom. Now we want to know the number, or the area of the atoms that are in the unit cell. So since we're doing area and we're treating all of our atoms as circles, the area of a circle is pi r squared. And you have to be careful here. How many atoms are inside this unit cell? Well, it's made of 4 atoms, but not all of each of those atoms are in. It's only a quarter of each atom is in the unit cell. And there are 1, 2, 3, 4 quarters. So 4 quarters adds up to a whole. So if I take those 4 pieces, it adds up to 1 whole atom. So 1 whole atom, that's the area of 1 whole atom, pi r squared. So when I take the numerator, the area of the atoms within the unit cell, which is pi r squared, and I divide it by the area of the unit cell, 4 r squared, excuse me. Notice that, and then I'm going to multiply it by 100% to get a percentage. Notice that r squared cancels out, numerator, denominator, and I'm left with pi over 4, which happens to be about 79%. That's the packing efficiency. That's the amount of that's the percentage of atoms filling up that unit cell. So about 21% empty space. That's what we're going to do. Now, let's do 15. How are we going to do this? So I want to do this together because this is a little hairy for people that haven't done geometry in a while or trigonometry. We have a different arrangement of atoms. So instead of being lined up one on top of the other, we have kind of offset rows, right? We have a row here and a row here, and they're shifted over. So the unit cell, you could draw a unit cell where you have the corner of the unit cell in the 4 atoms, and you've got one whole atom inside the unit cell. Well, let's find the area of the unit cell first, and we're going to do it with respect to the radius of the cell, of the atoms. And it's not 2r, because here's one radius, here's another radius, and there's this gap in between, which is hard to measure. Like, I don't know what that is. So another way we're going to do that is, what about if we use Pythagorean's theorem? We have this diagonal here, right? And the diagonal, how long is the diagonal in terms of radius? Well, there it is right there, 4r. 1, 2, 3, 4 radius is long. Well, according to Pythagorean's theorem, if you have a right triangle, so a triangle with a 90-degree angle, a squared plus b squared is equal to c squared. So what that means is, if this is side A, and that's side B, that's side C, the long side. So if I take a squared plus b squared, it's going to equal to c squared. I'm going to simplify things a little bit. A and b are the same length, right? It's a square. It's what comes from a square. They're the same length. So instead of a squared plus b squared, I'm just going to say a squared plus a squared is equal to c squared. That becomes 2a squared is equal to c squared. And the other thing I know is that c, the length of c, is 4 pi, or 4r, excuse me. The length of the diagonal is 4r. Okay? So I'm going to replace c with 4r. If I do that, what do I get? I get 4 squared is 16, r squared is r squared. And now I'm going to solve for a. I want to know what is the actual length of one side of the unit cell. So I'll move 2 over here. I get a squared is equal to 8 r squared. I divide both sides by 2. I'll do the square root of both sides. And if I do the square root of both sides, I get a is equal to square root of 8 times plain old r. So you square root both of these, you get square root of 8, and then you get r squared is, square root of r squared is just r. So I just calculated what the length of one side of a unit cell is in terms of the radius of the atoms. It's radical 8 times r. Radical 8 is about, what is that? 2.7, something like that, right? Anyway. Okay, so now let's find the area of the unit cell. The area of the unit cell is 2 times that, right? Or not 2 times that, it's this squared. It's side A times side A. And so if I square this, I get 8r squared again. I didn't have to do that, actually. So there's the area of the unit cell. It's 8r squared. All right, I've got my denominator now. So now I need to know the numerator. That is the area of the atoms inside the unit cell. Well, how many atoms are inside that unit cell in total? Well, there's one whole one right in the middle. Inside this unit cell, there's one whole one.
There's another whole one.
And there's a second whole one, if you add up the corners, yeah. So this quarter plus this quarter plus this quarter plus this quarter adds up to one whole one as well. So there's a total of 2 atoms inside that unit cell. And what is the area of an atom? It's pi r squared. So the area, or the area of the total number of atoms inside the unit cell is 2 times pi r squared. There's 2 atoms. Each one is pi r squared area. We're going to divide that by the area of the unit cell times 100%. And then look at this. R squared cancels out again. And I'm left with pi over 4. I get that the same thing again? I guess I did. All right. Pi over 4. There we go. So it just by coincidence, this has exactly the same packing efficiency as the last arrangement of atoms. Okay. Now we're going to do the same thing in 3D. Let me be clear. All of this geometry that we did, I'm not going to make you do it. It might be extra credit maybe, but it won't be an actual question you're going to get asked. The meaning behind packing efficiency, you will. And there's going to be a calculation we'll do later that you'll have to do. But I'll show you what that is. So, that's basically how we calculate a packing efficiency. So let me remind you that your solids can be crystalline or amorphous. We're going to focus on crystalline, right? And crystalline are, what? Oh, I didn't turn it on. That's why. I'll turn it on in a second. These are crystalline solids, or anything that has this well-ordered structure. You can define at a small level, and it repeats that pattern over and over and over again. That's what we're going to focus on. But just be aware that there are plenty of solids that are considered to be amorphous, where there's no real structure to them. Glass is a very common one. Rubber, most plastics are like this. They are definitely solid. They just don't have a well-ordered structure. So we're going to focus on crystal lattices, or crystals, crystalline materials, and we're going to use unit cells to describe the crystal lattice. So what is the crystal lattice? This is the geometric arrangement of lattice points in a crystal. We're going to use the word lattice points instead of the word atoms, even though a lot of the time you can replace the word lattice points with atoms. The atoms are here. I'm going to say the lattice points are here, because sometimes you can have molecules in those lattice points too, okay? So it's a position in a crystalline structure. That's what the lattice point is, okay? And the unit cell is the smallest box-like unit from which you can construct a crystal, okay? So we already see this. Although we're going to start to see this with 3D now. So in chemistry, or I guess this is any field that uses crystals, there are actually 7 different crystal systems that we can use to classify crystals. And then, of course, that breaks down into lots more. But 7 basic ones. These are the 7. We have cubic, tetragonal, orthorhombic, monoclinic, hexagonal, rhombohedral, and triclinic. You don't have to memorize these, but just kind of notice the difference. So with cubic, it's a perfect cube. A and B and C are all the same. Length with height. Everything's got 90-degree angles. It's a perfect cube. And you can start having variations on that. So A and B might be the same, but C is different, and everything still has 90-degree angles. Here, A, B, and C are all different, but they're all 90-degree angles. And then you can you can start changing that. A, B, and C are all different. 2 90-degree angles. The third one's not. It's angled now. You can have this weird hexagonal one. You can have like triclinic. Everything's different. 3 different angles, 3 different lengths. It's a weird. I forgot what you call the 3D parallelogram, but it's all funky.
Parallelepiped.
What's that?
Parallelepiped.
Is that what it's called? Okay. Well, we call it triclinic crystals. Okay. All right. So, fear not, we're only going to focus on one of these. The simplest one, cubic. Cubic crystal systems, okay? So, makes the math a lot easier, makes looking at these things a lot easier. You'll see a few extra in lab next week. Yeah, next week's lab. But for tests, cubic only, okay? So, like I was saying, you could actually subdivide these 7 crystal systems into smaller divisions. And the primitive lattice for each one of these is one in which you only have lattice points at the corners of these boxes. So if I go back to this, if I have, for instance, an atom here at these corners only, and that's it, nothing inside, That's what we call the primitive version of these crystal systems. Every one of these have a primitive one where you just have atoms at the corners. But then you can start doing stuff like adding lattice points on the faces in the middle of these. Like if you have the box, a box has 6 faces, right? You can put a lattice point in the middle of the face. You can put a lattice point inside the box. You can put lattice points on the edges where the faces meet. There's lots of ways to kind of have more complicated versions of these crystal systems, all right? And so we're going to look at a couple different examples. And so again, we're going to only focus on cubic unit cells. So simple cubic, sometimes also called primitive cubic. This is the one that's the most simple. This is the one where you only have atoms at the corners. And I kind of want to run out and go grab some models real quick. So hold on 1 second. Grab these. I'll be right back. Okay. So, this is simple cubic. Get a perfect cubic shaped unit cell, and there is in this case you could call it an atom, but it doesn't have to be an atom. It could be a larger molecule, but there is something sitting at the corners of these lattice points. We also have something called body-centered cubic. And body-centered cubic looks like this. So ignore the actual connections. I mean, you can't have this floating in space. It has to be connected somehow. But the positions are what matters. We have all the corners, just like simple cubic, but we also have one right in the middle, right inside. This is what's called body-centered cubic crystal systems. So, finally we have something called face-centered cubic. That is face-centered cubic. So we have the corners positioned, just like before. We do not have the body-centered position. There's nothing in the very dense center. But we have an atom, in this case, at every face position. So at every face of this cube, there's something smack dab in the middle. So there's 6 of them. So these are the different crystal systems that we're going to kind of focus on. I don't know if you guys want to touch them, but feel free to go and look at them. No rush. So there you go. That's the pseudo 3-dimensional drawing of it. You might be thinking, do we have to draw these? Do we have to learn how to draw in 3D? No, we don't. Because as chemists, we have ways to draw these crystal systems using 2-dimensional drawings, not perspective drawings like this. And I'll come back to how we do this in a second. So notice that you can either have the crystal structure shown like this, or you've got these little tiny balls just showing the positions, or you can kind of show it more realistically. So this is kind of how the space-filling model looks, where you represent the atoms that are in those spots realistically, how big they get. They take up space. They butt up against each other. So this atom, which is only partly inside this unit cell, is butting up against this atom, which is only partly inside this unit cell. You've got here one in the dead center butting up against the corner atoms. And then here you've got these face atoms butting up against the corner atoms. That is a face-centered cubic, yep. All right. So, before we get into the main stuff, let me introduce this. This is how we do a very simple diagram for these structures. This is what's called a layer diagram. And there, you can either draw it like this, or let me show you an alternative that looks almost the same. But first, let me explain how to get them. So a layer diagram shows slices, horizontal slices through the crystal structure, through the unit cell. And you're only going to have slices that will actually pass through a center of an atom. So this is simple cubic. This is the simplest one. There's only atoms at the corners of the cube. And remember what the nature of a unit cell. They have to be repeatable. So if I have a crystal made up of a bunch of these, the next unit cell is right on top. And the bottom layer of the next unit cell is exactly the same as the top layer of this unit cell. So if you think about it, in any unit cell, the bottom layer is exactly the same as the top layer. And that's what we're showing here. We're showing z is equal to 0, that's the bottom layer. Z is equal to 1 is the top layer. And anything in between, you'll use fractions. So halfway through, 3/4 of the way up, 1/4 of the way up. So use fractions. But the z equals 0 layer and the z is equal to 1 layer is always going to be the same. You don't have to draw it twice, actually. You could draw it once and then just do 0, 1, because it's always going to be the same. Now, other ways to draw it are, you can draw a layer here. This represents the bottom of the unit cell. And you can just draw the part that's inside. There's atoms at the corner. And you don't have to do space filling. You can do, as long as you indicate, hey, there's an atom here, here, and here, and here. That's what matters. You wouldn't put anything in here because there's no atom in the center. If you kind of take a look, here, let's actually go through this a little bit. Yeah. So z is equal to 0 and 1 are always the same. If you go to the worksheet, there's a whole bunch of pretty diagrams. Yours are probably not in color, but here we go. So here is simple cubic. That's the layer diagram for simple cubic. We're only showing one layer because the bottom layer and the top layer are the same. But notice what body-centered cubic looks like. We have two layers. We've got the bottom layer, although it's also the top layer, 0 and 1. But then there is a slice through the middle, because if I slice through the middle, I go through the middle of that central atom here. And how do we show it? Well, it doesn't have to be this big, it could be smaller, but there is an atom in the center of the unit cell in that slice. So layer diagrams are going to be tricky because you're going to have to understand when you're looking at a corner atom versus a face atom versus a central atom. Does that kind of make sense? So if I put a circle here, and I'll show you, let's go to the face-centered cubic. Here's the layer diagram for face-centered cubic. Notice I've got my corner atoms in layer 0, the bottom layer, but I've also got an atom right in the middle there. That's the face atom. That's the one sticking out from the bottom right in the middle. So on this one, that's this one right here. And that one's half inside and half outside the unit cell. And then I go to the halfway up. I cut through the middle, and I've got atoms on the other faces. And then the top layer is exactly the same as the bottom layer. So drawing these layer diagrams is going to take a little practice and getting used to. You'll have a lot of practice in the lab next week, let's put it that way. All right, so just like before, when we start talking about dimensions, how big these unit cells are, it helps to have the dimensions in terms of what atoms we're using, the radius of the atom that we're making this unit cell out of, this crystal structure. So when you see R, we're talking about the radius of an atom. When you see S, that's defined as the length of one side of the unit cell. And we're only doing cubes, so they're all length with height, same thing, okay? So you're going to have different equations, whether it's simple cubic, body-centered cubic, or face-centered cubic. Just like with the 2D structure, we came up with like different ways to calculate the length of a side. And I guess I should show you this. So let me give you another kind of saying what I just said before, but different words. This helps. And we got to sit through a commercial, unfortunately.
So I've got my essay written, and I've been working on it for about a week. So now I'm going to show you how I use Grammarly to edit. Okay, so here's my essay, and I'm going to click through Grammarly suggestions in the right panel.
And then, 1 second. Oh God, it's so slow. Okay.
If you could travel within a crystalline solid, you would see the particles, atoms, ions, or molecules arranged in a regular array. Here, the spaces are greatly exaggerated, but in reality, the particles are packed close
Let's
together.
try it again. Hold on.
The unit
It should be coming out of the speakers instead of here.
If you could travel within a crystalline
Alright, never mind.
solid, you would see the particles, atoms, ions, or molecules arranged in a regular array. Here, the spaces are greatly exaggerated, but in reality, the particles are packed close together. The unit cell of a crystal structure is the smallest portion that defines the structure. Stacking unit cells next to each other in all three directions gives the structure. Many elements and simple compounds have unit cells from the cubic crystal system. Let's examine the three types of cubic unit cells. All cubic unit cells have particles at the corners of a cube. The simple or primitive cubic unit cell has particles at the corners only. In reality, the particles lie as close to each other as possible. Note that the particles touch along the cube edges, but not along a diagonal in the face or along a diagonal through the body. By slicing away parts that belong to neighboring unit cells, we see that the actual unit cell consists of portions of the particles. When the cells pack next to each other, in all three dimensions, we obtain the crystal. If we fade the others out, you can see the original group of 8 particles within the array and the unit cell within that group. We find the number of particles in one unit cell by combining all the particles' portions. In the simple cubic unit cell, 8 corners, each of which is 1/8 of a particle, combine to give 1 particle. A key feature of a crystal structure is its coordination number, the number of the nearest neighbors surrounding each particle. In a simple cubic array, any given particle has a neighboring particle above, below, to the right, to the left, in front, and in back of it for a total of 6 nearest neighbors. The body-centered cubic unit cell has a particle at each corner and one in the center, which is colored pink to make it easier to see. With full-size spheres, you can see that the particles don't touch along the edges of the cube, but each corner particle does touch the one in the center. The actual unit cell consists of portions of the corner particles and the whole one in the center. 8/8ths give 1 particle, and the one in the center gives another for a total of 2 particles. In this tiny portion of a body-centered cubic array, you can see that any given particle has 4 nearest neighbors above and 4 below for a total of 8 nearest neighbors. The face-centered cubic unit cell has a particle at each corner and in each face, which are colored yellow here, but none in the center. The corner particles don't touch each other, but each corner does touch a particle in the face, and those in the faces touch each other as well. The actual unit cell consists of portions of particles at the corners and in the faces. 8/8ths at the corners gives 1 particle, and half a particle in each of 6 faces gives 3 more, for a total of 4 particles. In this tiny portion of a face-centered cubic array, notice that a given particle has 4 nearest neighbors around it, 4 more above, and 4 more below, for a total of 12 nearest neighbors.
Look familiar from the lab? Yeah. So you guys now can kind of recognize, hey, I was looking at FCC unit cells in the lab, and you get the 12 coordination number. Not always. It doesn't always mean that, but in this case, I'm pretty sure it was. Okay, let's stop there. Yeah, that's good stuff. So, being able to count the numbers of atoms inside the unit cell is another critical skill. Just like we did for 2D, you're going to have to do this for 3D. And the answers are right there. You can memorize them if you want, or you can just remember and just be able to understand how this works. Faces are always, the atoms are half in and half in a neighboring cell. So faces count as half an atom. Corners count as 1/8. If you look at any of these cubic crystal cells, this atom here is in this cell, but it's also in the one right next to it. It's the one right here, and it's the one at the corner, plus the one on top, one over here, one here, one here. So there's 8 unit cells that share this one atom. So it's only 1/8 inside this particular unit cell. And there's 8 corners. 8 times an 8 is one whole atom. Okay. So let's try questions 16 through 20 on the connectivity thing. I'll let you guys work on those. So I want you to be aware that the equations that you're going to need are in this diagram that's kind of preceding. Notice that we have the side of a, so S is the length of one side of the unit cell, and it's 2R, 2 radiuses. So we've got all these equations for these different crystal systems, so you don't have to figure them out yourself using geometry. Although that one's pretty easy, but the other ones are a little trickier. So we've got them listed. So yeah, 16 through 20, please.
Different densities. Like, I imagine you could probably have some with missing a corner or something like that. Oh, but it'd have to be repeatable.
Yes, for the most part. Yeah, we're going to get to imperfect crystalline structures, like doped it with other materials. We'll get to that eventually. But and then the density question is really interesting because we can literally calculate density on an atomic level and have it come out perfect for our level. It's pretty crazy.
Oh, that's pretty crazy.
Yeah, we'll do that next actually. So. I haven't seen them, no.
She's pretty good actually.
Huh. I haven't watched that
You already watched the writer.
one.
I just got that question. Senator Cubic. Or was it Senator Cubic? Zero one and then the yeah, no, I know the equation for it, but I mean, I guess for the equation for the, oh, so you just use the 4 over 3 by our side, or the sphere, and then
Oh, no.
yeah. Well, I don't know how to put that either. Yeah, I don't get it.
Which one?
20.
So, if we're doing volume, if I know the side of one, the length of one side, how would I do volume?
Well, maybe not.
It's a cube, perfect cube.
Which is
and
that?
Oh,
radius.
just radius, oh, of the perfect.
So just of the perfect cube, if I know the length of one side, I would do what? Cube with the sides, length times width times height, that would give me the volume.
Okay. So just for like.
So if I know the side, I just cube it,
Oh,
right?
okay.
Right? So now, I know the side in terms of the radius, do the same thing, cube that whole thing.
Oh,
That makes sense?
yeah, that makes sense. So instead of just like. Yeah.
Yeah. In this case, yeah, it's, we'll use it later, but, not right now, just yes.
We're just not gonna like the whole thing. This is just a side. Kind of like, like this is the equation member for like the Pythagorean theorem. And he's bringing it, he's trying to make this measure as a sphere. Now it makes sense. You're right that that sphere is like,
That's a basic equation, but why is it easy?
So remember, for a generic perfect cube, the volume of the cube is length times width times height, and if they're all length s, it's just s cubed. But that's not what we want in question 20. We want in terms of r. But we have equations for that. It's on the previous page that tells you how s is related to r. All right, we'll talk about this in a second. Oh, let's talk about it now. Might as well. I think people are like getting it or not. So, 16 names simple cubic, body center cubic, face center cubic. Whether you write them lowercase or uppercase doesn't matter. 17 is just copying those equations from the other page. 18, y is only an eighth of an atom at the corner. Well, the way you explain that, yeah? Want to give it a shot, or? Okay. I thought I heard somebody say something. All right. It's being shared by 8 different unit cells. If I put you on the spot, I'm sorry. So this corner atom is shared with 8 other unit cells. That's why it only counts as 1/8 for this particular cell. And then a face atom, like this one, is in this unit cell, and it's in the one that's right next to it. That's it. It's not in any others. It's shared by 2 unit cells. So it's half in this one, half in the other one. And that's why they count for half. If I had one on an edge, like right here, even though there's nothing here, it would count as, it would be in 4 unit cells. So it would count as a quarter. Right? It would be in this one, it would be in this one, it would be in this one, and then the one that's kind of diagonal. Although we're not going to see that today. We'll see it in the lab. And then the body center cubic. This one, it's only in this unit cell. That's it. So that's why it counts as one whole atom for this unit cell. It's not shared with anything else. Okay, so for 19, simple cubic, how many? Just 1? Body center cubic? 2? Face center cubic? 4. So the corners count as 1, and then there is 1, 2, 3, 4, 5, 6 faces. Each count as a half. So 6 times a half is 3. So the 3 from the faces plus the 1 from the corners. That's 4 total atoms. So 4 for FCC. Before we get to the next one, by the way, I kept saying that we don't call these atom positions, we call them lattice positions, because this is frozen carbon dioxide. Anybody tell what crystal structure this is? Face center cubic. It's hard to see, but if you focus on just the carbon part, so this is CO2, carbon with 2 oxygens. Focus on just the carbons. There is a carbon at the corners, here. And then there are carbons at the faces. So here, and the bottom, and the top. This is face center cubic, but this is CO2. And instead of atoms at the lattice positions, it's an actual molecule. This is a molecular solid in this case. So that's why we call them lattice positions and not anything specific.
That's pretty cool.
There's a couple oxygens missing, like I pulled out, I think, but this one right here is missing one. But other than that, it's pretty good. Oh, no, that one too, yeah. That one too, you're right. It's an old model. Okay. So for 20, it's, I kind of brought this up because you're going to use this as a basis for figuring out how to write the volume of the unit cell, the different unit cells. So if you go back to the equation, for simple cubic, a side is 2r. Well, the volume is the side cubed. So if I cube this, 2r cubed, I will get the volume. And so 2 cubed is 8, r cubed is r cubed. There's your volume, 8r cubed. For body center cubic, a side is 4 radical 3 r. So the volume is going to be that thing cubed, which is a little bit tougher to do. 4 times 4 is 16, times 4 is 64. Radical 3 times radical 3 is 3, times another radical 3 is 3 radical 3. You guys remember that from algebra? And then r cubed is r cubed. There you go. And then face center cubic, the side is radical 8r. And so the volume is going to be radical 8r cubed. So 8, radical 8 cubed is 8 radical 8. And then r cubed. I did that fast. So radical 8 times radical 8 is 8. Times another radical 8 is times, you can't combine them unless you want to write decimals.
16 radical
Oh, you can simplify it, sure. 16 radical 3. No, yeah, radical 3.
You're right.
Oh, you're right. Sorry. You're right. 16 radical 3. You're right. But anyway, this particular math, this is busy work. I'm not going to ask you this in a quiz either. So on a quiz or an exam, we would give you these volume formulas or side formulas, okay? So you don't have to memorize them. Don't worry about it. If you need them, we'll give them to you. Now, well, I won't turn the quizzes on for this one, but, well, actually, why not? Here, this is just kind of sticking into your head. How many atoms are found in these unit cells? All right, so excellent. 1, 2, and 4, not 1, 2, and 3. So number 20 we just did. Trying to stop this. Here we go. And so you get these results, and yeah, you could simplify FCC a little bit more than that, but that seems to work. So now, let's do questions 21 through 23 together. And they're going to get a little bit hairy, so I'm going to go slow. So, yeah, let's do that. Let's go right to the worksheet. There we go. So 21 is determine the packing efficiencies of each unit cell. So this is another thing that I'm not going to ask you to calculate directly on an well, no, that's not true. I could ask you to calculate this, but I will give you some of those equations. So how do you calculate packing efficiency? Instead of area, we're going to look at volume. We're going to calculate the volume of the atoms within the unit cell. We're going to divide it by the volume of the unit cell itself. So we have all these numbers already, or at least the equations. The volume of atoms, or actually let's do the denominator. What is the total volume of the unit cell per sample cubic? It's right there. That's the volume of the unit cell. 8r cubed. Now, what we need on top is the volume of atoms within the unit cell. And the volume of a sphere is right there, 4/3 pi r cubed. How many atoms do we have inside simple cubic? Just one, total. So it's just going to be 1 times that. 4/3 pi r cubed. And I'll just times 1 specifically so you can see it's just 1 atom in there. Notice that the radical 3's cancel out. Oh, and I forgot, it's times 100%. And when you do the math here, I think it comes up to 51% or 52. What is it? 4 divided by 3 times pi divided by 8, 52%. I'll be more specific, 52.4%. That's the packing efficiency of simple cubic. There is a lot of empty space in a simple cubic crystal system, which might lead you to think maybe it's not common because it's wasting a lot of space. And we'll see the truth in a little bit, okay? So that's the packing efficiency of simple cubic. Let's do body center cubic. All right, well, how many atoms are inside body center cubic? There's 2, so 2 times the 4/3 pi r cubed volume of a sphere. And the unit cell volume is right here, 4 over radical 3, no, sorry, 64 over 3 radical 3. R cubed. So, times 100%. This goes away. And we've got a little bit of a mess, but 4 over 3 times pi times 2 divided by 64. Oh, I should have done, all right, divided, well, you'll have to be careful how you do this. So 64, let me do this again. Store that. So 64 divided by 3 radical times radical 3 is 12, and if I do the numerator divided by the denominator, there we go, I get 68%. So notice slightly higher packing efficiency. That should make sense a little bit. I mean, maybe it's hard to see without space filling models, but this has less empty space than this does. This has more empty space, okay? And then finally, FCC, 4/3 pi r cubed times how many? There's 4 atoms inside a face centered cubic. The volume of that unit cell is 8 radical 8 r cubed. All right, and then finally times 100%. Radical 3, sorry, not radical 8. R cubed, radius cubed, cancels out. 4/3 times pi times 4 divided by 8 times radical 8 in parentheses. And I get 74%. So notice the packing efficiency is going up as you get to these other crystal systems. So FCC packs a little bit more densely, tightly. There's less empty space. You do not have to memorize these numbers either, but you should memorize the order at which the packing efficiency increases. Okay, so FCC is going to have the highest, simple cubic is going to have the lowest. Okay. All right, that's 21. 22. If we were to calculate the molar mass, if we were given the molar mass of the atoms that make up our unit cell, how would you figure out the mass of the atoms within the unit cell? So, what is molar mass? What are the units of molar mass?
AMU.
AMU is technically not molar mass. When it's a molar mass, the definition is slightly different. It's the mass of 1 mole.
Oh, yeah.
Remember that? So the units are going to be grams per mole. So it's the number of grams, whatever that atom is, for 1 mole of that atom. That's in a lot of atoms, right? A mole is a lot. How do we shrink it down to grams per atom?
Just turn it to
Yeah, Avogadro's number. So remember, Avogadro's number is the number of things in 1 mole. So in this case, we're counting atoms. So 6.022 times 10 to the 23 atoms. So notice that moles will cancel, and I'll be left with grams per atom. We can get the weight of 1 atom, basically, in grams. So if I know there's 1 total atom, because it's simple cubic inside the unit cell, I can calculate the mass of that 1 atom. If there's 4 atoms, I can just take this number and multiply it by 4, right? So I can get the mass of all the atoms inside the unit cell. That's what's going to let me do number 23. So 23, this is the linchpin of it all. Well, not linchpin. It's the goal. We're going to calculate the density of lead. But instead of using the traditional method of calculating density, you get the mass of a chunk of lead, and then you figure out its volume, and you do mass over volume. We're going to do it on the atomic scale. We're going to take the mass of all of the lead atoms in a unit cell, and we're going to divide it by the volume of that unit cell. And that should give us exactly the same density as we're used to. Alright, so what are the units of density that we were used to? What is, generally? Sorry?
Joules? Oh,
That's energy.
oh,
Density, it's mass over volume. What are the units of mass we usually use?
kilograms.
Well, grams usually for chemistry. Even kilograms is standard. Grams are usually used. And what about for volume? What's a comfortable volume that we've used? Liters is good, but centimeter cubed is usually, so when we do a density, it's often written as grams per milliliter or grams per cubic centimeters, okay? So the goal is, let's get a value of grams per cubic centimeters. So we want, in the numerator, the mass of the atoms inside the unit cell. And for down here, we want the volume of the unit cell. And that'll give us the density. So let's calculate these pieces. All right, what do we need to know? Well, we have, first of all, we're given that it's lead. So if I know it's lead, I can calculate the mass of lead atoms. How many lead atoms are there going to be inside this unit cell? It's 4 because I've been told it's an FCC unit cell. So because I know the way lead packs together, I know there's going to be a total of 4 atoms inside the unit cell. So let's start with this equation here. What's the molar mass of lead? It's Pb, 207.2. This will give me the the grams per atom. And I know that there's going to be 4 atoms for every 1 unit cell. Yeah, so atoms will cancel, and I'm left with grams per unit cell. So what does this come out to? Let's see. 207.2 divided by 6.022 e to the 23, and then times 4 atoms. So the mass of those atoms inside the unit cell is going to be 1.376 times 10 to the minus 21 grams per unit cell. I can leave that up. I know what this means. It's per unit cell. All right, let's do the second part, the volume. What do I know? Do I have the radius of the lead atoms? No, but they gave me something even easier. They gave me S, the length of one side of the unit cell. It's 4.9505 angstroms. So if that's the length of a side, what's the volume going to be? That cubed. Easy. But let's make it a little easier. We eventually want centimeters, not angstroms. Angstroms is a unit that literally means times 10 to the minus 10 meters. It's a very convenient unit for dealing with atom sizes. That's where it comes from. But let's convert those angstroms to meters, to centimeters first, to make the calculation easier. 4.9505 angstroms. So for every 1 angstrom, it's 1 times 10 to the minus 10 meters. And I don't want meters either, I want centimeters. So to go from centimeters to meters, 1 centimeter is 1 times 10 to the minus 2 meters. So if I do this right, it is 4.9505 times 10 to the minus 8 centimeters. There's your length of a unit cell. But I don't want length, I want volume. So the volume is 4.9505 times 10 to the minus 8 centimeters cubed. It's the size cubed. So, oh, that's not it. Hold on a second. 4.9505 e to the minus 8 cubed. 1.213 times 10 to the minus 22 centimeters cubed. That's a volume. It's a really tiny, tiny volume, but we're dealing with atom scale, right? So that's fair. So I have the volume of the unit cell. I have the mass of the atoms inside the unit cell. I'm ready to calculate density. So there it is, 1.376 times 10 to the minus 21 grams over 1.2132 times 10 to the minus 22 centimeters cubed. Let's see, x over that last number is 11.34 grams per centimeters cubed. Now, that seems reasonable. Let's look up what the actual value is online, because the internet's always correct. Usually pretty good. Look at that. Right on the money. So it's pretty crazy that we can use crystal structures to kind of get these macro scale measurements that we're used to. Right? Density is something in intro chem. We literally weighed something and then we dumped it in a graduated cylinder with water. We measured the change in volume of that water, and that's how we got density. Now we're doing it using atom scale measurements. Where did this number come from, this angstrom? Well, X-ray crystallography. So you take a perfectly grown crystal of something, in this case a piece of lead, and you shoot X-rays at it. And you guys remember 221 when we did diffraction patterns. What happens when you have regular spaced openings and you shoot light through it? It diffracts, right? It makes a pattern. That's what happens with perfect crystals too. X-rays will go through these perfectly spaced atoms and do these diffraction patterns, and we can use computers to take the diffraction patterns at various angles. We have to do it at a lot of different angles, and the computers will reconstruct what the crystal structure is. It will tell you exactly how far apart the atoms of your crystals are, and you can literally measure these things from a computer screen after you've done this kind of analysis using X-ray lasers. Pretty interesting. So, yeah, we can literally calculate density from atom stuff. So I think that's one of the coolest things about this. So this kind of calculation is something you should be able to do. It's a little overwhelming, I think, at this point, but when you practice it a few times, it will get better. We'll do another one of these, I think, on Thursday. You'll see it in homework too. So make sure that this kind of calculation makes sense to you. We got an easy one. We were given the length of the side of the unit cell. You could also be instead given the radius of a lead atom. And then you'll have to plug that into this equation instead to find, to find the volume of the unit cell instead of the way we did it here, which is cube the sides. Okay? So, be careful, read with the problem carefully so you understand which equations you need to use. All right. So, let's kind of reiterate what we learned. The order of the unit cells in terms of increased packing efficiency. Spot on. Okay. This isn't that hard. It's just a little overwhelming. It's brand new information, so hopefully it sticks. That's the critical question. If you'll remember it next week. And you don't have to know these numbers, but these are the same numbers we calculated. You can find them anywhere in the literature, in our worksheets and the textbooks. So, yeah.
So why don't? Oh, that's the packing efficiency, but ultimately the density is then mainly regulated by the mass of the atom at that point.
Yeah. So, okay, let me give you a real world example. So, iron. We did the blacksmithing. We did the tempering and hardening and all that. Iron goes through several different crystal structures. So we didn't talk about it in terms of this type of structure. We talked about it in terms of the grain size, which is also relevant. But when you heat iron, iron can go through different crystal structures as well. I think there is a low temperature phase where it's body-centered cubic, and then when you heat it up to a certain temperature, it can rearrange to make face-centered cubic. And then there is a newer, even higher temperature structure that is body-centered cubic again, but larger size of the unit cell. So the unit cell size is slightly bigger. And so just that will change the density of iron. And that's not even including that you don't have perfect metal, you don't have perfect crystal structure all the way through.
Right, sure.
So there's a lot of factors. So here we're assuming perfect crystal structures, right? So, but it works, right? Lead density is pretty spot on. Yeah. Anyway, yeah. So remember, anything we learn is very simplified. It's good enough, but it is simplified. We're making a lot of assumptions when we talk about some of these things. Okay. All right, so we did this, and yeah, there it is. There's the formula for density, mass over volume, but we did it on a micro scale or atomic scale rather than the macro scale. There we go, we got it. So here's the calculation again, in case you missed it. This is on the PowerPoint slides. There is the generic how to get the mass in grams of a unit cell. And these are the units involved. So you should get the same units. Very, very simple. Not really, but it looks simple on the slide. Maybe it doesn't. I don't know. It's all dimensional analysis. Let's put it that way. Okay, so I'm just going to make sure you understand that the stuff you'll get quizzed on is knowing how to take a side and given the side and the volume. So you'll be given the equations for the side and or the volume of the unit cells, and know how to use them to calculate things like volume of a unit cell. You need to know how to do layer diagrams. So not this quiz, next week's quiz, okay? But we'll practice that in lab next week also, so you'll have a little bit of practice. I guess right before. Yeah, it'll be it'll be before the quiz, so you'll have time. Knowing how to calculate coordination numbers. So if you're looking at something and saying, oh, that has 6 nearest neighbors, that has 8 nearest neighbors, that has 12 nearest neighbors. That depends on the type of unit cell. How to order the packing efficiency. You don't need to know the numbers, just know what the order is. And then how to do this kind of density problem. And backwards and forwards. So here we calculated density. Could you take a density and go backwards and calculate the side of a unit cell? Things like that, okay? So calculating the actual packing efficiency, or calculating volume equations from side equations, I mean, that's not that bad, but that's just math. So those are extra credit, okay? So yeah, you don't have to ever come up with those on your own, let's put it that way. So I mentioned that simple cubic is probably rare because it's wasting a lot of space. That's kind of true. So when you're talking about the elements of the periodic table, there's only one element that actually has this simple cubic packing structure, and that's a super poisonous one, polonium. You guys are all too young, I think, but 20 years ago, maybe not that long ago, an ex-Russian diplomat who defected to England was killed with polonium by, we think, is the FSB. I think they put a little bit of it in his tea, but I think there was a different story of also, maybe it was a different guy. They stung him in the leg with a needle that had polonium on it, using like the needle was attached to an umbrella. Anyway, you get this in your system, and it's just going to slowly kill you over the period of months, and you will die. It's like the worst thing in the world. It's awful. But anyway, polonium does simple cubic. Notice that a lot of them do body-centered cubic, the green ones. Face-centered cubic are the blue ones. Look at that gold, platinum, all the fancy shining metals. And then one we're not going to talk about. There's plenty of others that do other types of packing. So this is that weird hexagonal shape packing, which we're not going to cover. You'll see it in the lab as an example, but we're not going to worry about that for an example. But again, there's plenty of other packing arrangements for non-elemental stuff. So we're talking about ionic compounds. We're talking about other covalent networks like gemstones and stuff. Like they all do slightly different packing arrangements. Okay. But metals tend to like high packing efficiencies. And high packing efficiencies means high coordination numbers. Why would they be happy being next to a whole bunch of other atoms? Well, they don't care about their electrons as much. Okay, so metals are unique in that sense. Here is an iodine crystal. Can anybody tell what the packing arrangement is for iodine crystals? It's a little hard to see. I don't know if I can tell actually. Yeah, it's really hard to tell actually. might be primitive. No, it's not primitive because it's going the other way. Yeah, this one's hard to tell. I think though it's face-centered, actually. I feel like it has to be face-centered because
It's
if you
3
look,
and 2 and 3 and 2.
yeah, it's 3. So this is in front, that's in front, that's in front, that's in front, that's a corner. And then there's the third one in the back is a corner, back of the corner, back corner, back corner. Oh no, doesn't work.
No.
It's something else. Anyway, yeah, it's kind of difficult sometimes. But the CO2 one, that's pretty clearly FCC. So molecular solids pack in a crystalline format to iodine is a natural crystal at room temperature. Here's methane. This one's clear. And again, treat methane, even though it's not super complicated, but it's not a simple sphere. Just think of it as being spherically shaped. And you can see that it kind of does FCC packing. You get your corners, and then your face. There's a corner, face, corner. So where do you get solid methane? Moons of Jupiter, I think Jupiter. Places that are cold enough and have a high enough pressure to create snow, methane snow. I'm sure there's science fiction movies that have shown that, but it's for real.
So with something like this, we would, if we were going to calculate the mass or the volume, or the density,
The density,
we would just replace the grams per mole with the total of the molecule itself.
Yep. And then if we knew either the side or the radius of the molecule, we could use that and the fact that it's FCC to get the volume of the unit cell. Yep. All right. So we've looked at metals, and we're going to get to ionic compounds later. It's a little bit more complicated. We've seen molecular solids, the extreme cases. What about the semimetals in between? So what's going on? How do they pack together? How do they make structures? So notice that this thing is saying that metals are this cubic diagram. They're metallic. These are all covalent molecules. You can make solids out of them, but they're molecular. This thing is saying that these semimetals, and that includes carbon, even though carbon is not a semimetal technically, make these things called covalent networks. So, which we saw in the lab today. Why covalent networks? Why not more metallic type structures? Why not more molecular solid type structures? So let's look at carbon and just kind of talk about, and carbon's going to be generalized for all the semimetals. So the atoms are not very big. They're intermediate to small size. The bonds are fairly strong. They're not weak like metals are. They're not super strong like fluorine makes bonds, but they're high to intermediate electronegativity. And the result is that these things will want to do pretty strong interactions with their nearest neighbors. If they have a pretty good electronegativity, then they're attracted to neighboring electrons, and they're going to have a really strong interaction with their neighbors. The problem is, and so the bonding is going to be more localized, right? So, when you make an interaction with a neighbor, that electron sharing is going to be pretty permanent, and it'll be stuck like that. Like the electrons won't be able to move around. Like in a metal, the metals can have lots of neighbors because it doesn't really matter where the electrons are. They can be anywhere. The electrons are more free to move around. But when you have this slightly higher electronegativity, the bonding is more directional. They're localized. And so semimetals and carbon, which is kind of a lowish, medium to high electronegativity, are really restricted in the number of nearest neighbor interactions they can have. Think about carbon. When we learned covalent bonding, the rule of covalent bonding and Lewis structures is you want to have an octet, and that's it. They want to have 8 electrons, and that's it. So when we looked at how carbon makes bonds in a Lewis structure, carbon can make at most how many bonds? Just 4. It's already got 4 valence electrons. It wants to share with 4 other atoms at most to share 4 more electrons and get 8. So carbon and the semimetals tend to have similar interactions with neighbors. They are limited in the number of neighbors they can have. But because they can do, so like carbon can do 4 bonds, you can get really directional. You can have a neighbor this way, you can have a neighbor this way, you can have a neighbor in 3 dimensions. Whereas something like fluorine can make 1 bond and that's it. And it's not going to make this large extended structure. So it's a balance of things like that that cause these covalent networks to occur. So here's another picture of the electronegativity. Here's carbon, which is not as low as the semimetals, but it's near. And you could argue phosphorus does similar things, and maybe selenium does, and it's true, they do. So because of they're in that middling electronegativity, they do this kind of covalent network. And so here's what silicon looks like. Silicon, like carbon, does 4 bonds. And so the coordination number of silicon is 4. And that's it, only 4. Notice, so how do we describe, and this makes a crystal structure. Silicon makes really crystalline structures. So how do we build this crystalline structure using the models we've learned? Because simple cubic has 6 nearest neighbors. 5 cubic has 8 nearest neighbors for each atom. And FCC has 12 nearest neighbors for each atom. Every atom is near 12 other atoms. So none of these work for this kind of crystal structure that we need for silicon and carbon and the other semimetals. So it's something else. And since we're not going to do any other crystal systems, there must be some weird modification going on to the ones we've already learned. And that's kind of what it is. So here's diamond. And
What did the CN stand for on the previous slide?
coordination number.
Oh, thank you.
Sorry, yeah, number of nearest neighbors.
Yeah.
So we already know that diamond is 4 single bonds, and or the carbon has 4 single bonds, and in diamond those bonds are in tetrahedral arrangement. It's really difficult to see. This is going to take a little extra time to grab. It's all in the lab. I'll be right back.
I'm making diamonds for lab. Make diamonds for lab next Tuesday.
Did you ever do the experiment when you were a kid where you made like crystals? You know what I'm talking about.
Yeah.
That was some school. That was like art science and stuff.
Yeah.
They kind of do crazy experiments now for our curriculum, like the stuff they actually like online schools and stuff. They
Mhm.
send that.
All right. So that's diamond. Sorry. So this is diamond. Ignore the outer ones because that's it's not showing everything. But if you look at any of the inner atoms, every atom in the middle, every one of them, even the corners of this thing, has 4 nearest neighbors. So how would you describe this? So I'll show you in a second, but here's how we describe it. We start with FCC, which is not the whole picture because FCC, sorry, I'm out of shape. Every single atom in here has 12 other nearest neighbors. So that can't be right. So take FCC, spread out the atoms a little bit more, so there's more room in the inside. And then there are these spots that happen that are called holes. So these slightly larger areas inside, they're called holes. These particular spots are called tetrahedral holes. And that's what TD stands for. And they're called tetrahedral holes because when I put an atom in one of these spots, suddenly this atom has only 4 nearest neighbors now. And if I include the tetrahedral holes, even the sides and the corners suddenly only have 4 nearest neighbors now. So that's what a tetrahedral hole looks like. And notice that there is 4 in this top layer, and there's 4 in this bottom layer. So in a layer diagram, that's 0. The middle is 1/2. This would be about 1/4, 0.25. That would be about 3/4, 0.75, when you label what the layers are. So these hole positions, there is a total of 8 of them. There's 8 tetrahedral hole lattice positions when I separate the FCC structure out a little bit. So if I zoom in on one of these positions, this front top right position, and I highlight, well, which atoms are nearest to this tetrahedral hole. I isolate that one, and you can kind of rotate that a little bit, and these are literally in the tetrahedral shape, 109.5 degree angles. So what you're looking at here, and I'll pass this out, is the pink marks off one of the unit cells. So you've got your corner atoms here, here, and here. You get your face atoms, and this is the atom directly inside a face. There's 6 of them. And then finally, on the inside, and they're marked with white tape, are the tetrahedral hole positions. Now for diamond, so let me come back to this. In general, for an FCC structure, any FCC structure, there is a total of 8 possible tetrahedral holes. All right, there's 8 holes. That's the lattice positions possible. But I want to be clear that for diamond, only half of those positions have atoms in them. So notice that in the top layer, instead of having all 4 tetrahedral holes filled with atoms, only half of them, 2 of them have atoms in them. The other 2 are empty. And then in the bottom half, or bottom quarter, there's only 2 atoms in those 4 tetrahedral hole positions. And that's what we see here. So there's only 4 atoms on the inside that are covered with tape. These 2 here, and these 2 here. I'll let you guys look at it more closer if you want. But that is the diamond structure.
For diamond, only half have tetrahedral holes.
So for diamond, there are 8 tetrahedral holes positions, but only half of them have atoms in them. Right, so half are filled with atoms, carbon atoms, half are empty. And if you look, that's the only way you can get this perfect. Everything has tetrahedral. Everything has 4 nearest neighbors, and it's like this throughout. So if I were to do a layer diagram, it's a little bit harder to see, but this is what it looks like. You have an FCC structure overall. So remember what FCC is. FCC is corners and faces filled. That's basic FCC. So your bottom layer, layer 0, has the 4 corners and the face. There is the face atom, there's your corner atoms. Halfway through, you've got just 4 faces. This one, this one, this one, and this one. That's these. And then your top layer is the same as your bottom layer. In addition to those basic FCC structure, you've got the holes. So 1/4 of the way up and 3/4 of the way up, half the holes are filled. So there is a spot here and a spot here where there's nothing. But this spot has an atom, this spot has an atom, and then it's alternated on this side. And the next level up.
So if all 8 were filled, what would it be called then? Just crazy.
It's not the diamond structure anymore. It probably has a name, I don't know it. But it's still FCC, you would say, with all the tetrahedral holes filled. That's all, if you wanted to describe it. But this is the diamond structure. And the reason we're going over this is you're going to see this structure repeated quite a bit for even the semi-metals. So silicon does this. I think germanium does this. And we're going to see some crazy stuff. So you've already seen how we can take a metal and a non-metal and make a bond that makes it similar to semi-metal properties. So gallium and arsenic actually is more semi-metallic than anything else. It turns out gallium arsenide has the same structure. It has this diamond-like structure. And somehow this diamond-like structure gives us all the properties we need to make things like LEDs and other things. So this is one of the important structures. It's really basic, but it's one of the more common important structures that we need to study. Now, just to give you an idea of the differences, that's diamond. This is graphite. So this is carbon also. This is an allotrope. When you have different structures but the same element, they're called allotropes. And the way diamond looks is it makes these hexagons. So you might be thinking, well, there's only 3 bonds. Where's the 4th bond? Well, remember these are like 1 1/3, or it does the resonance with. So there's a bunch of single and double bonds mixed together that makes these layers. And notice that it makes layers. So there's a layer of graphite, a layer of graphite, a layer of graphite. If I take some real graphite, I wish I had some, and I put a piece of Scotch tape on it, and I peel that Scotch tape away, I will be left with a really super thin layer of graphite. Because graphite comes apart in layers really, really easily.
Are those double bonds why graphite is conductive but carbon's not?
So it's partly, yes. So the double bonds that exist in the ring, it's because remember we have the p orbitals that stick perpendicular and they're kind of all parallel to each other. And the electrons in those p orbitals can just move around. And the mobile electron is what makes it conductive, yeah. It's crazy. So it's rare. It's rare that you have conductive nonmetals like this, but it happens. Okay. I think I went a little fast today because I'm running out of time. That's it for this. Yeah. Let me see the next set of slides. And I don't know if we want to go to the next one yet, but let's see if there's enough that we can do. I think we're going to lose a day eventually because of a teacher training pressure.
The week of the 23rd. We don't have a Tuesday lecture, is that right?
Is that it? Yeah. What is that? How many weeks ago now is that?
Tuesday.
Oh, it's a
We're
little.
in week 2 now, that's week 4.
Okay, so it's a little ways away.
And
Okay.
that's just before exam 1.
Yeah. So we will lose a day then, but we'll catch up. All right. Let's see. Oh, this is annoying. Come on. All right. Yeah. So let me just show you this, and then we'll stop. So these are not my. Oh God, they don't work anymore. No, yeah. they broke. That's what you get for. Oh, their website's broken. That's why. Maybe they're not fully broken.
So how do you get something like a ruby laser? Because that's a crystal.
A what laser?
A ruby laser.
Oh man.
Or does it have? If it has nothing to do with these crystals.
No. So okay. We'll stop here, but let me talk really quickly. I don't know too much about geology. I'm not a big geology person, so natural stuff I don't know a whole lot about. But a lot of these gemstones are really basic crystals. So they're built on quartz or corundum. I can't remember.
Says right there.
Is that? Oh, is it there?
Yeah.
That is corundum. Yeah, that is. What happened? IMDb. Yeah. Oh, there it is. So you were talking about aluminum oxide. Ruby is basically aluminum oxide. That's the base. And aluminum oxide by itself is, I think, just clear, transparent. But what makes it red is that it's not a perfect crystal. It's got, let's see, it's not gold inside. It's something else. What is it?
Chromium?
Is that what it's, did you see that?
Yeah.
I think it is chromium. You're right.
It's up on the side banner. If you scroll up a little bit more.
Oh, there it is. Yeah. Yeah. So it's got some chromium in it. I think this probably has a lot of chromium, but it's hard to say. Yeah, there it is. So, yeah, that's what gives it the color, and it's the transition metals that make the pretty colors. Everything else is pretty boring white. That's why I like transition metals. So yeah, you know, ruby is basic corundum, which is, I think, kind of a junk stone, but once it's been doped with chromium, it's suddenly super valuable, assuming it's clear and perfect and, you know,
Yeah, very, very
all those things.
well built.
And a lot of these things we know how to build, like from scratch, including diamonds. We know how to make diamonds from scratch.
It's pretty darn difficult.
So,
right?
so it used to be a lot more difficult, but now there's places that can do it really easily.
Oh yeah.
And you know, so the value of these things is completely artificial. Like the synthetic diamond is, they're the same. They're exactly the same. I think they probably made a deal with De Beers, the diamond company in South Africa, to dope their diamonds with a fluorescent thing, so that they could quickly identify whether they're fake or not fake, but artificial or not.
Huh.
So they have machines that will find the fluorescent tag inside,
Just darn capitalists.
and it's all artificial, because otherwise you could flood the market with nice diamonds that are just otherwise not naturally made.
Indistinguishable from natural diamonds.
Sorry, what?
They're indistinguishable from natural diamonds.
I mean, if you didn't, well, they might be too perfect. That's probably part of it. Because the way they do it is they start with a seed crystal.
Yeah.
So they start with a really, really super thin piece of diamond, and they stick it in a vacuum chamber, and then they pump in these gases at a high pressure and a high temperature, and it's a chemical reaction that will basically convert whatever the gas is inside to pure carbon, and that carbon in gas form will naturally find the most appropriate position on the already existing diamond that's in there, and it'll just grow it. And so you can see time-lapse videos of these things, and it just looks like this little plate, and suddenly it's gotten really thick, and it looks black, it looks disgusting, but then when they polish it, it's pure diamond on the inside.
Wow.
Yeah, so if you build it the right way, it's indistinguishable. It's just probably it's too perfect sometimes.
Yeah.
So yeah, I know for sure that they put little micro engravings on them sometimes. I know sometimes they put fluorescent tags in them so that when you hit it with a certain kind of light, you can see this marker that glows and says, hey, this is synthetic.
Yeah.
But otherwise, they're exactly the same. There's nothing different about them.
Cool.
Yeah, which is great for tool industry because diamonds are really hard. It's good for making saws that cut really hard things. Yeah, and so same with all these. I mean, you can grow them. I mean, that process I described. I can show you the video. It's pretty neat. It's one of the intro videos that we didn't do.
What, growing diamonds? You need to show us that.
Mm-hmm.
It's probably
Just to kind of be like, hey, this is cool. Hold on. I'll show you a clip, and then you can go back and look at it yourself. Oh, you know what? I hit it. That's why. Hold on. Delete.
True. How would you? I suppose you could get a really high pressure chamber.
I mean, the exact process to make them as perfect as they are is trade secrets.
Oh,
You know,
okay.
but. All right, this is Neil deGrasse Tyson. Let me.
Oh, really? So it's not something you do in your backyard, huh?
No, you
Like,
need
go to a
here.
lab
Let me
experiment.
show you.
What are you up to?
I don't know. I mean, this is pretty lucrative. It seems
So
like.
there you go. There you got like a vacuum chamber that looks like that. Little ports so you can see what's going on. You pump in the right gases and the right heating element. Here, let me get. This is a little old, so I'm sure there's other ways to do this now. Yeah.
If you look on the internet, will they show you the unit cube or whatever it's called? Yeah, the formula unit. Will you show you the formula unit on a
Okay, there you go. So, yeah, chemical vapor deposition.
Is
3 or 4,000 degrees Celsius plasma. So a mixture of gases. If you don't know what a plasma is, it's so hot that now the electrons have separated from the atoms, and it's like a soup. It's like a metal now. It's like so yeah, the diamond seed creates the pattern, and then these atoms come in and find, hey, this is the perfect place for it to be, and it just continues growing that same pattern. And then they're growing. Time lapse.
Then can you like break off the top and reuse the base?
I don't like
Yeah, I mean they just take a slice and reuse it. Yeah.
Is it growing little diamond nuggets along the side too?
Yeah, yeah.
That's cool.
And then they look like garbage at the beginning, but see, it looks like
There's
teeth.
a little bit.
So knowing this, did you buy your wife a diamond ring?
We don't have diamonds. so-
Yeah.
Yeah, and so after they cut them, they look good. So I mean,
Funny.
That's pretty dang cool.
yeah. Yeah, no, we were busy paying for med school.
Important
and
things.
trying to survive. With 4 kids, we had twins at first, so it was pretty hard.
I know someone who just bought their now fiance probably like a $40,000 diamond ring.
We'll get some money
That's
going.
just like stealing money, but.
True.
I mean,
Factor for sure.
I didn't go, but my wife went
Yeah, something you
to
have the material.
a
Look, I got
$150,000
carbon,
wedding.
right?
Oh,
And I'm like,
yeah.
why would you pay that much money for a wedding? Like, this is the stupidest thing ever. Just buy a house or,
Yeah,
you know,
essentially.
give them a down payment.
It's a way bigger payoff.
Yeah, no.
The return on the investment there.
I mean, I'm sure she wouldn't mind a diamond ring, but we have plenty of other things we want before that. So.
You could do that right now, just start today.
Well, I suppose you could. True, these are doing the right
What would
way.
be even cooler is if you just made it for her.
I already built our deck and our pizza oven and all the other stuff in the backyard, so.
That's awesome. What is it, a fake diamond? I'll take
Fake
pizza oven
diamonds.
any day.
So fake diamond in my mind is cubic zirconia. That's fake diamond. Cubic zirconia. That's the other sparkly white rock that, which they can tell immediately it's not diamond, but I mean they're still nice looking. Yeah. Rarity and exclusivity. That's it. Yeah.